When we talked about a uniform circular motion, we have decided that we only have one type of acceleration, which is the centripetal acceleration, that is in minus r hat direction. So the acceleration only has a radial component, and there is no tangential component. Now, if we talk about a particle moving along a curved path, now in this case we will see that the acceleration will have both tangential and radial components. So here is an example. You can see here this particle is moving along this curved path, and we can draw a circle here and a circle here and a circle here, and you can see that in this curved path I can draw these many circles, and for each circle I can define a radial unit vector r hat, which points from the center towards the particle, and there is a theta hat, which is tangential to the motion of the particle, the path of the particle. Now, the acceleration vector will have two components, the radial acceleration and tangential acceleration, and the total acceleration is the sum of these two. And why do we need to have a tangential acceleration? Because as opposed to uniform circular motion, in this case, the speed of the particle is changing, and we need to have an acceleration that is going to account for this. So for this purpose, we need to have a tangential component. Now, the total acceleration is the tangential part plus the radial part. And as I said, the tangential part is responsible for a change in the speed of the particle. Now, if we go back to our analysis, the velocity vector, the tangential velocity, is in the theta hat direction, and it has a magnitude v, which is the speed of the particle. Now, the total acceleration is the rate of change of the velocity, so it's dv dt. So if I take a derivative of v theta hat with respect to time, the first part I will have v dot, so it's going to be v dot theta hat. Then I will have plus v theta hat dot. So that's the time derivative of theta hat. V dot, as you know, is dv dt. It's the rate of change in the speed of the particle, which was normally zero in our uniform circular motion. In this case, it's not zero. And we have theta hat dot, and if you remember, we have found in the previous lecture that theta hat dot is minus theta dot r hat. So with that, we have dv dt theta hat, the tangential part, and minus v theta dot. Theta dot is the rate of change of angular speed omega. So it's going to be minus v omega r hat. Because v is equal to omega r, it's also equal to minus omega square r hat. So you can see that the total acceleration is dv dt theta hat minus v square over r hat, or minus omega square r hat. So we can talk about it in two different ways. So the total acceleration has the tangential part, which is dv dt, and radial part, which is minus v square over r. That is the usual centripetal acceleration that we see in uniform circular motion. How do I calculate the magnitude of the total acceleration? It's square root of a radial part squared plus tangential part squared, and I can find its direction. So if I look at the tangent of this angle here, so if you look at the tangent of this angle, that would be AR divided by AT. So let's put an angle alpha here to show the direction of the total acceleration, and you can see that tangent alpha is the radial part divided by the tangential part. Okay, so let's take a look at an example. The figure represents the total acceleration of a particle moving clockwise in a circle of radius 2.5 meters at a certain instant of time. Okay, so it's not actually moving on this circular path, it's moving on a curved path, but at a certain instant in time we find that it is part of this circular motion. The path is part of this circular motion. And for that instant, find the radial acceleration, the tangential acceleration, and the speed of the particle. So as you can see, we know the magnitude of the total acceleration, and we know that the acceleration vector makes an angle 30 degrees with respect to the radial direction, and it's going to have a centripetal part, so the component on this axis will be pointing towards the center, and the tangential part, which will be responsible for change in its speed. So the acceleration is minus 15 cosine 30 r hat, so it's pointing in this direction, and it's also, because we define the angle theta to be positive in the counterclockwise direction, it's also pointing in minus theta hat direction for the tangential part, so it's minus 15 sine 30 theta hat. So we find its components. There is the component here, and there is the component here. So we can now read the radial acceleration. It is the centripetal acceleration minus 15 cosine 30 square root 3 over 2 r hat, which is roughly minus 13.0 in minus r hat direction meters per second square. The centripetal acceleration is v square over r as a magnitude. So 15 square root 3 over 2 is v square over r, and we know that the radius of this circle is 2.5 meters, so we multiply 15 square root 3 over 2 with 2.5, take its square root, we find 5.7 meters per second for the speed of the particle at that instant. Once again, this is not a constant of the motion anymore. And for the tangential acceleration, we have to look at minus 15 sine 30, which is minus 7.5 theta hat in meters per second square. So we can determine these quantities at that instant in time for the motion of this particle. Okay, now we're going to change gears. We'll talk about a different type of motion, which is the relative motion. So relative motion means we're trying to describe the motion of a particle from a different reference frame. So what is a reference frame? A coordinate system with respect to the origin of which an observer is at rest sets up a frame of reference. We can talk about the lab frame, we can talk about the particle reference frame, etc. So a simple example is here. We want to report the position of this particle at point P. And on this axis, you can see here, we label 0 point A, minus 5 point B, and plus 5 point P. So if I ask you what is the position of this particle P with respect to an observer at point A, so you put a reference frame coordinate system here, and at the origin we have an observer who is watching the particle at point P, and he or she will report plus 5. If I do the same thing for point B, I put a coordinate system here. At the origin, the observer sits and watches the particle, and because we have to move a distance 5 and another 5 plus 10 meters to point P, this observer will report the particle is at plus 10. Okay, so the position of point P is measured by two different observers. Point A observer says it's at plus 5, point P observer says it's at plus 10, and these x-axes are with respect to the origin, defined with respect to the origin of these points A and B. Okay, so as you can see, these observers are reporting different numbers for the position of the particle. Now, I'm going to talk about two different cases for these reference frames. One case is that we have a reference frame at rest, so SA is at rest, and then we have the B reference frame is moving at a constant speed. This is the velocity of the B reference frame with respect to A reference frame, and it is a constant velocity. It's moving on the x-axis, let's say, and if I report the position of a particle at point B, according to reference frame A, this particle has a position vector Ra with respect to the origin, and according to an observer that is moving at constant velocity Vba with respect to the A reference frame, will report the position of the particle at Rb, and as time goes by, the origins of these reference frames are going to be uh, going away from each other with a velocity VBA, so it's VBA times t. So at t is equal to 0, I'm assuming that SA and SB reference frame coincided completely. The origins were the same, but then the B reference frame started moving with constant velocity VBA. Okay, so SB is moving at a constant speed VBA in the positive x direction. So what is the relationship between the position vectors reported by the A observer and B observer? So you can see from this diagram that the position of the particle at point P as reported by an observer on reference frame A is VBA times t, this vector, plus the position vector reported by the B reference frame observer, RPB. So if you take this equation and take a derivative with respect to time, then we will be reporting the velocity of the particle. And the rate of change of position in the reference frame A is d dt RPB, the rate of change of position as measured by reference frame B, and then we have the derivative of this one with respect to time, that is VBA plus t dVBA dt. Because we have a constant velocity and constant speed, this is going to be 0. So you can see I call the velocity of the particle as reported by observer A is UPA. The velocity of the particle as reported by observer B is UPB plus VBA. So you can see that there's a relationship between the velocities reported by A and B. It's if you look at the velocity reported by B, add to it its velocity relative to reference frame A, you get the velocity reported by reference frame A. If I take one more derivative of this one, duPA dt is dupB dt plus dVBA dt, but VBA is a constant, so it's going to be 0. I will find that the accelerations that they will report, acceleration reported by A and acceleration reported by B, are exactly the same. So this set of equations 1, 2, 3 that transforms the position reported by two reference frames, velocity and acceleration reported by two reference frames, are called Galilean transformation equations. And in the case when a reference frame is moving with a constant speed in reference to another reference frame, we find that it's going to have the same acceleration reported. So the two reference frames measure different velocities for the particle, but they measure the same acceleration when VBA is a constant. Now let's look at another case. The B reference frame is accelerating with respect to A reference frame. At t is equal to 0, the origins coincided. So if I do the same exercise, as time goes by, at t is equal to 0, because the origins coincided, the origin of point B has moved away a distance 1 over 2 at squared in time interval t. So Ra, the position reported by A reference frame, Rb, position reported by B reference frame, have a relationship. Rpa is 1 over 2 at squared plus Rpb. So these vectors add up. Then if you look at the velocity, UPA is the derivative of this one with respect to time at, because the derivative of acceleration with respect to time is 0. I'm assuming constant acceleration. Plus UPB. And if you look at the acceleration, one more derivative with respect to time, now I see that even the accelerations reported by these two reference frames are not the same. So if SB is accelerating with a constant acceleration A with respect to SA on the x-axis, then we have this set of Galilean transformation equations, which tells us that the acceleration reported by the two reference frames, the observers on two reference frames, are also not the same. Let's quickly look at an example. A boat crossing a wide river moves with a speed of 10 kilometers per hour relative to the water. So we have a water reference frame, and the boat is moving with a speed of 10 kilometers per hour with respect to the water. The water in the river has a uniform speed of 5 kilometers per hour due east relative to the earth. So the water reference frame is moving due east, so this is east, so it's in plus x direction, relative to the earth with a speed 5 kilometers per hour. So this would be our VBA. If the boat heads due north, determine the velocity of the boat relative to an observer standing on either bank, this bank or that bank, which means we're looking at the earth reference frame. Now, here is our earth reference frame. Here is our boat reference frame, the river reference frame. The river is moving, the water is moving with respect to the earth reference frame with a relative speed VRE. So this is our VRE vector, and it's in plus x direction, so it's due east. And we are trying to report the position of the boat from the earth reference frame, from the water reference frame, and the water reference frame and earth reference frames origins are moving in time t a distance VRE times t. So I look at the position reported by the earth reference frame, that's this one for the boat. It is VRET plus the position of the boat reported by the river reference frame. If I take a derivative with respect to time, the velocity of the boat reported by earth reference frame is velocity of the river reported by the earth reference frame, I hat direction plus velocity of the boat with respect to the river. So you can see that the velocity of the boat with respect to earth is velocity of the river with respect to earth in I hat direction. Since the boat is moving due north, so that is with respect to the water, we have VBR J hat for the velocity of the boat. So what is the velocity of the boat with respect to the earth? Well, this VBR J hat, that is the velocity of the boat with respect to the river. VRE I hat, that is the river moving with respect to the earth reference frame. And we find the total velocity vector here tells us the velocity of the boat with respect to the earth reference frame. So if the boat heads due north, because the water is moving to the right, then observer on this bank or on this side would report the boat is diverting from the north by an angle theta. It's moving to the other shore here if you are reporting from here, but it's not moving on a linear path, on a direct path towards this bank. It's actually moving away from it. Okay, so if you plug in the numbers, the speed of the boat with respect to the earth will be square root of VRE square plus VBR square. Remember that the river is moving with respect to earth at 10 kilometers per hour, so its square is 100, and the boat is moving with respect to the river at 5 kilometers per hour. Square root of, so it's going to be 25, square root of 125 will give me the speed of the boat, 11.2 kilometers per hour. And you can see that tangent of this angle theta, VRE over VBR, is 5 over 10, 1 over 2, which tells us the angle it makes with the north direction is 26.6 degrees. Or I can say that the velocity of the boat with respect to earth is VRE I hat, 5 I hat plus VBR J hat, 10 J hat, and it is measured in kilometers per hour. So this is what I was supposed to determine. Okay, so this was a simple exercise for this case where I have a reference frame is moving with constant velocity with respect to another reference frame, and these two reference frames are not reporting the position, but they're reporting the velocity of a particle that is moving with respect to both reference frames. So in this case, we had a boat that was heading due north, but because the river was moving at a constant speed with respect to the Earth reference frame due east, we find that the boat actually moves with respect to the Earth, making an angle theta with respect to north, and its velocity vector can be found by looking at the velocity vector with respect to the Earth of the river, VREI hat, and plus the velocity of the boat with respect to the river, VBR J hat, gives me the answer that I'm looking for.